So let's briefly talk about what an electric field is. This is Physics 1C for September 1st. So an electric field is the idea that when you have charges fixed in space, they produce effects on the space around them that can be felt by other electric charges. So if you have a charge that we call big Q, and this charge is fixed in place, we define an electric field due to a point charge as being, if I come out to some distance where the distance is usually defined to be r, and technically it's a vector. If I really want to do this, it's a vector that points like this from the source charge out to the point, then at this location we say that there's an electric field that exists, and the size of that electric field is equal to k times q, well, I'm using big Q, right? So be k times big Q divided by r squared. And then you can also, if you want to add in a directional component to it, you can put r hat above this to define that there's a unit vector that points along the r direction that we call r hat, okay? And that is our electric field at this point right here, basically, okay? And technically, I guess, if I really want to do this right, looking at the picture doesn't look quite right. We would want to do this, and then move this kind of up to, like, right there, basically. It's the proper way to do it. So this is the definition of the electric field of a point charge. It says that all around the point charge, this thing exists. And we're going to use this idea to talk about different systems, like a line of charge, a ring of charge, a disk of charge. You should probably mute your mic, whoever did that. That was definitely a burp. All right, so we're going to use this to look at how to solve problems, for example, like this one right here, where we have a positive charge Q distributed along a line of charge. And I want to say some general things about how we're going to handle these problems. So when you have systems where you have what we call continuous charge distributions, continuous, that's not how you spell it. This is as opposed to discrete charge distributions. A discrete charge distribution would be like you have one charge here, another charge here, another charge here. That would be a discrete charge distribution. You've got a bunch of different charges, then I ask you, okay, what's the electric field at this location equal to? That's an example of a discrete charge. A continuous charge distribution is when you have like a line and it's completely charged. When we're dealing with these type of systems, we have to define the electric field in a slightly different way. We have to define it in the following way. We have to say that for an individual piece of our object, we're going to define the electric field that gets produced to be given by this. So we're going to basically be splitting our object up into tiny little pieces. So dq is going to represent a slice of charge from our charged object. And we're gonna define this dq in a way so that we can do this integral. In order to do that, what we're going to have to do is we're going to have a set of rules for how we define what dq is. And there's going to be three different possibilities. When you have a charge that's distributed kind of across a line or a curve of some sort, we're going to have what we call linear charge density. And the symbol that we're going to use for this is lambda. Okay, that's effectively what we call charge per unit length, basically, right? Lambda is going to represent charge per unit length. The units for this are going to be like coulombs per meter. Remember that a coulomb is a unit of charge. The unit for charge density is going to be coulombs per meter. So like, just to give you an example, let's say you have a rod, and I tell you that the rod is 2 meters long, and I tell you that it contains charges. Okay, so it's got some charge, and I tell you that that charge is uniformly distributed. That means throughout the rod, you've got a certain amount of charge per unit length, right? And then I tell you that on this charged rod, that the amount of charge that we have is something like 4, let's say, microcoulombs per meter. Okay? That would tell us that if I took any piece of this rod, no matter how big, this tells you how many charges per unit length you get. So I could ask you questions like, what's the total charge on the rod? What would that be? What would the total charge on the rod be? If I've got a rod, and I tell you it's 8, right? And you got that by doing what? You just take, you basically saying that Q total is equal to the charge density multiplied by the length. Let's call this the length of the rod here. Lambda times L. That would give you, yeah, and so like what Ash put in chat, you do 2 meters right here. You multiply by 4 microcoulombs. And that gives you, like he said, Q total is 8. No, whoops, that was bad. Let's put it like this. Q total is 8 microcoulombs. That's simple enough. I could ask a question like, suppose I cut the rod into 4 pieces, right? Let's use a different color. Suppose I cut the rod in half, and then I cut the rod in half again. How much charge would there be in this piece? So I cut my rod into 4 pieces, right? So now you've got, in this little piece right here, you've got 1/4 of the charge, right? Because you cut it into 4 parts, right? So 2 microcoulombs. That tells you that it's uniformly distributed, right? That's basically what this says. Every meter, you get 4 microcoulombs. Okay, does that make sense to you guys? That's linear charge density, okay? We also define things like surface charge density. Okay, the symbol we use for this one is sigma, and the unit for this, you can probably guess, since it's a surface density, is going to be coulombs divided by meters squared. This would be like, suppose that I have a plate, and on this plate, I have charges uniformly distributed throughout it, and I say, on this plate, maybe there's 4 coulombs per meter squared, and I say that that's defined as sigma, and then I tell you how big it is. Maybe it's 5 meters on one side and 5 meters on the other side. You could find the total charge by finding the area and then multiplying by this, right? What would the total charge on this guy be? 100, right? Yeah, 5 times 5 is 25 times 4. You get 100 coulombs, right? Pretty simple. The thing is that when we start to introduce this type of thing, I think people get it confused a little bit, or at least I did when I was learning this, is if you have this dq now, what is that going to mean? Well, we can actually relate this dq to these lambdas and something to do with length or area as well. And the way that we normally do that is by saying that an infinitesimal piece of charge, in the case of like linear charge density, if I have, let me move this down just a little bit. Yep, plenty of room to work here. So if we're talking about this thing dq, if I want to know what dq is in the case of something that has linear charge density, what we're going to do is we're going to say that dq is going to be equal to lambda. Now this is a charge per unit length, so we have to multiply by a length, right? Except what we're going to do is we're going to say, suppose that I have this object and it's a rod and it has charges. It has charges, and I say, I want to know that if I take my object and I split it up into pieces, like up here we split it into 4 pieces, right? And we said there's 2 microcoulombs. But what about instead of splitting it up into 4 pieces, what if we split it up into 1,000,000 pieces, or an infinite number of pieces? If we do that, then we can cut out from this object some amount of charge that we call dq. It's still charge. I mean, the d might confuse people. It might, if you start thinking about calculus, maybe that bothers you, but it's some amount of charge that's actually contained within this rod. And if I tell you that this rod carries a charge per unit length lambda, now remember, lambda is just a number. It's a constant in this case. If I want to find the amount of charge contained in that location, then what I can do is I can say, let's define the thickness of this object to be dx. And if I know the length of the piece that I'm cutting out, then if I take the charge per unit length and I multiply by that length, then I get the charge, right? I get the charge. So this is a really useful equation for doing these problems, because after all, we're ultimately trying to find electric fields, and one of the things we're going to need to be able to do is to eliminate dq from our equation and write it in terms of some other variable, basically. Remember, k is just a constant. Now, the other type of thing that we're going to have is we're also going to be able to talk about like surface charge densities. So with surface charge density, what we do is we say, I've got some object. It's got charges distributed throughout it, okay? And what I'll do here is I'll cut out a piece of the object, like maybe some piece right here. Okay, and I say the piece that we cut out we call dA. Why dA? Because it's like an area. Could be dx times dy in some situations, for example. And then here what we say is the amount of charge contained in this is going to be dq, and that our dq is equal to something times dA. What's it going to be? It's going to be sigma, because that's charge per unit area. That doesn't look like a sigma. Sigma. So these two equations are going to be really useful to us in doing these problems. They'll be useful to you guys too as you're doing your homework problems, including the problems that are on. There's problems on mastering physics. Those are whatever. They're going to be related to what we're doing. But what's harder are the problems that show up on your homework, on the lab manual homework in particular. So hopefully at the end of the day we can kind of start talking about this a little bit. Maybe even spend some in-class time working about them. No, we'll be doing things with 3 dimensions too. Yeah, and in 3 dimensions, which is what I would have gotten to. I'm not going to worry about that for now because it's not going to apply for a little bit, but for 3 dimensions, it's pretty easy to guess what comes next, right? You add a 3rd dimension, then instead of having dx or dA, you're going to have dV, okay? And if I have volume and I want to relate that to charge, then I need to have something here, and usually what we use is rho. So this would be for 3-dimensional objects, like maybe a cube of charge or something like this. And rho stands for volume charge density, basically charge per unit volume. Charge per unit volume, right? Okay. Even in the case of dealing with such systems that are 2-dimensional, we're going to produce 3-dimensional systems too, by the way, Ash, in order to understand them. Okay, so to summarize, what we've got is these 3 equations: dq equal lambda dx, dq equal to sigma dA. This is used for 2-dimensional cases, and then this one, which is used for 3-dimensional cases. This one's also going to be used later on for a lot of other things, talking about volume charge density. And our starting point for a lot of these problems is going to be this. Okay. So that's in general kind of a rundown, these boxed equations here, what we're going to need. The first problem we do is just need the 2 red boxes here. We'll just use those 2 equations to solve for this one. Okay, so that's the setup for what we're going to do here. We're going to do a lot of calculus to make this work. So just if I'm going too fast at any point, or if you get lost as to why I'm making a step, just please feel free to cue your mic or say something in the chat, because everything that we do tonight there's a lot of details, and if you miss any of the details, you can go back and watch the video on YouTube, I suppose, but now is your opportunity to ask, right? So don't be afraid to ask. So field of a charged line segment. Positive charge Q is distributed uniformly along the y-axis between y equal to negative A and y equal to positive A. We want to find the electric field at a point P on the x-axis at a distance x from the origin. So for this one, what we're going to do is we're going to draw out as best we can what we're trying to find here. So we have a y-axis, we know that, right? So let's drop in a coordinate system. We're going to need like a full coordinate system like this. So there's going to be our coordinate system. Let's make it black. So we got a coordinate system, and oh boy, it loves to herk and jerk around, doesn't it? There we go. Move that a little bit. So we've got our coordinate system, and it says that we have positive charge that's distributed uniformly along the y-axis. So let's make a rod to represent this. We're going to have a rod here. It's positive, so we'll make it, is that like even? Something like that, maybe. Didn't do anything. I gotta turn this thing off, I think. Okay. Basic shapes. Let's try that again. Red. It doesn't like it when I pick the color second, does it? It just does some weird things. Okay, there we go. It's working now. I guess it's okay to make it that big. I don't know, maybe make it a little bit smaller. It's probably fine. Oh, come on. Really? Is it really going to do stuff like that? Alright, we'll make it that big. So there's our, that's our rod. And it's saying positively charged Q is distributed along this rod from a point that's from negative A to positive A. So this down here is going to be negative A. Let's write negative A. That's going to be y equal to negative a. This point up here is going to be... Can't get too close to it, I guess. This is going to be positive a. Okay. Oh, you know what I want to do, actually? I want to get rid of some of this so it doesn't want to click it. Guess I have to do this with this guy. Okay, there we go. I'll do that by itself. All right. So our goal is to find the electric field at a point P that's on the x-axis at a distance x from the origin. Okay, so we're going to come out to some point right here. We're going to label that point as P, and then say that it's a distance x away from the origin. So this distance is going to be x. And x is going to be a fixed value in this problem, okay? That's basically the x-coordinate of this right here. I don't want to draw too much on this. Just the x-coordinate of this point is x, basically. We're at some point x on the axis. So our goal is to figure out what the electric field at this location is if we say that our object here is full of positive charges. We've got positive charges that are uniformly distributed throughout this. And it doesn't say it, but we're going to say that the distribution is given by this lambda thing. So we're going to say that the charge per unit length we're going to call that lambda. And we're also going to say the total charge is Q on the entire object. The object has a length of 2a, so we can even define what lambda is right here. It's Q divided by 2a. That makes sense to you guys? Charge uniformly distributed. The charge per unit length we're calling lambda, and we're going to say that it's equal to the total charge Q divided by 2a. All right. So now what we're going to do is we're going to cut our object into little pieces. So let's go ahead and do that. So we're going to break the object up into a piece. We're not going to take it from the very end. We're going to take it from some spot kind of somewhere in between. We're going to label the y-coordinate of that point to be y. So y is going to be this distance right here. That's y. X is the distance this way. And we're going to say the amount of charge that's contained within that little piece that we've written right there is going to be dq. I think it's safe to write it like right here. So the charge inside of that little blue piece, that's the amount of charge that we're cutting out of this. And the other thing we're going to say is that the thickness of this object that we're cutting here, since it's along the y direction, the thickness is going to be dy. So the thickness, which I'll draw like this, I guess, that thickness is going to be dy. It's like a small change in the y direction. And now what we're going to do is we're going to say, if this is in fact just an infinitesimal piece of charge, and we're not going to worry about the width of this, it's just an infinitesimal piece of charge. So what we're going to do, though, is we're going to draw a line from where that charge is located, and we'll use a straight line for this one. We're going to draw a line from the center of that little piece down to the origin, and we're going to call that R. Okay, so this is going to be R. I feel like I need to make these bigger. Let's do like, I don't know, 14 point. Didn't like that, did it? I got to select it first. Okay, so that's R. That little length along that line right there is R. Why am I calling it R? Well, because I'm thinking that one of the things we're going to need to do in this problem is we're going to need to use our definition as we defined above that relates the electric field of a point charge to this little slice that we took out here. Right? That looks like the electric field of a point charge, so we need this variable R inside of here. Now, after we do that, if we know that there's positive charge that's on this object right here, we also know at that point that there's going to be an electric field produced at point P. So if we ignore all the other pieces of our object right here, and we say we want to draw the vectors associated with this electric field right here, what's the direction of the electric field at point P? Does it point toward the charge, or does it point away from the charge, since it's positive? Do I want to draw a vector? Let's use green for electric field. Do I want to draw a vector toward the charge or away from the charge? Oh wait, that's right. So at this location, I would draw a vector, and it needs to point exactly away. And that vector, I want to make it long so we can do things with it. That vector right there, I'm going to call the electric field. And we're going to use the symbol. It is an electric field, so we'd want to use E for that. But it's kind of like an infinitesimal piece of the electric field. It's only one part of the electric field, the entire rod. So we draw a vector like that. Okay. All right. Then what we can do is say, let's label this angle right here to be theta. That means this angle right here is also theta. And say, it's going to be kind of hard to deal with the electric fields in this form because it's a vector. The point we assume is positive. No, it says it's positive. Positive charge. We're not making that assumption. It is positive. Are we about to linearize it? Linearize what? I don't know what you mean by that. Linearize the vector? Yeah, shadow on the x-axis. Sure. That's one way to think about it. We're going to find the components, if that's what you mean. That's the language we usually use, is we're going to find the components. That is also thought of as, like, putting a shadow on the x-axis. You forgot the name of the components. Can't believe you forgot something from physics. That never happens. All right. So we're going to break this up into two components. One that's going to point along the x direction. I kind of want to do the y direction first, but that'll probably work out. I'll just adjust it if I need to. So another shape going down like this. I think that should hit it okay. Yeah, it's pretty good. So we're going to break it up into components. And we're going to say that since this component points into what we're calling the x direction, or this is x and this is y, we're going to call this component dex, and we're going to call this component here dey. All right. So now what we want to do is we want to find the values of each of these. Okay. And we know, to start with, we can begin with this equation right here. So we start off by saying the value of dE is given by this. The electric field produced at this location, the magnitude of it is going to be k times dq over r squared. Dex, which is the x component, we can find by doing what? How is that going to be related to the dE? What's the component of dE? If I say dE times what gives me the x component here? Cos theta, exactly. So we put cos theta right here. And then you guys quickly should know then that if I want to do dEy, then I'm going to have dE sine theta. Just your standard breaking things up into components thing, which we kind of need to do because it's a vector. All right. So, all right, I think we have mostly everything we need to continue here. So we're going to start by working just on this one here. All right, so we pop in here the value of what we define for dE. It's k times dq. dq is the charge divided by the distance between the charge and point P, which is r, as we defined right here. And we've got our cos theta sinking around. So now is the part where we have to start doing some things. We have an integral in principle, right? We could technically integrate both sides of this, right? On the left-hand side, it would basically sum up all of the things that we've got. And if we did it over the entire rod, then we'd be left with just the x component, okay? The problem is we can't instantly do this integral. If we want to be really lazy, yep, that's definitely what we're going to do in Meowers. So I don't think we're going to do that. We're going to do something like that then. We look at this integral right here, and we say, well, I know k is a constant, so I think there's no problem in pulling k out. And we could be really blind and naive and just say, well, cosine theta and r squared, there's no q's in those, so we just pull them out of the equation, right? But that's not going to work very well, because if we consider, for example, a different piece of our object, like let's say we come to this piece right here, we're eventually going to be cutting out pieces of the whole object, a bunch of little dq's. If we picked another dq right here, and I draw a line back to here, I'm going to erase it, but you get the idea. One of the values, at least, is going to change between r and theta. What's going to change? If I pick this piece right here, is it going to have the same value of theta? If I choose this piece and I draw a line back to here, and I find a new vector, is the value of theta going to be the same or no? Nathan's saying both r and theta change. Is the value of theta, if I go from this point down to here, going to change? It has to, right? This theta looks like it's about 30 degrees. If I draw it from here to here, it's going to have about half the value, right? So theta changes. That's exactly right. What about r? Does r change if I draw a vector from here to here? It does, right? It's shorter, right? Okay. It'd be the shortest when we go to this point right here. So that means that actually, depending on which dq we choose, right, you're going to get different values of theta and r. Okay, so that tells us that we can't immediately pull those out of the integral. They're going to stay in the integral. So what do we need to do then? We need to do something like what Meowers said. We need to relate things to x and y, or we need to get theta in terms of x and r, something like that. Or we could just get everything in terms of theta as well if we really want to. It's entirely up to you what you choose to do. One of the first things we can do, though, is say, because the charge is linearly distributed, we can rewrite our dq as lambda times dy. Lambda was the charge per unit length, and if you multiply by dy, that's going to give you the charge dq. So that's the first thing that we're going to do here. We're going to plug in the lambda dy. Okay, and now we can start to see that there's a relationship between y and r that's pretty easy to see in the picture, right? What's the relationship between y and r? Remember, y is the kind of height of this triangle right here. There's a right triangle that's created with the sides are r, y, and x, right? So how could I write r in terms of y? There's multiple answers to this question. Or sorry, yeah, there's multiple ways. How is r related to y? Y cos theta. Yeah, that sounds right to me. Except it's more like sine theta, I think. Pasta. Something like if I take r times the sine of theta, that's what y is, right? Yeah, you're good. The other thing is what Ash said. The other option would be we could use the Pythagorean theorem and say r squared is equal to x squared plus y squared. That would work as well, right? So we kind of have two options now. We could either eliminate y. Sorry, we could either eliminate r in favor of y and sine theta, or we could eliminate r in terms of x and y. It's really just up to us what we want to do. Okay? So the question is, do we want to get rid of theta? Do we want to get rid of r? Do we want to get rid of what do we want to do? We got to get all three of these variables into the same thing, basically. We want to get rid of r. And the question is, do we get rid of r to get like, which one do we want to use then? Do we want to use the one that has the sine theta, or this one with the x squared and y squared? You want to try theta? You want to turn r into theta? I'm glad you guys are saying that. Let's do that. Okay. Either way works, by the way. I don't want you to think it doesn't. So if we do that, we're going to get r is equal to, let's put it as y times the cosecant of theta. Maybe that looks weird. Let's not do that. Let's just say it's y divided by sine theta. Okay? All right. Now I start to think, what if we wanted to make it so that we don't introduce a new variable? What if we don't want to introduce, what if we wanted to put r in terms of x and theta? Is that possible? Couldn't I also say that r is equal to x divided by cos theta? We can do that, right? Now the value of this is that x is a constant, right? This is constant. Okay, so that's kind of powerful. Pos is saying if we have y and dy, it would be easier to do the integral. We're gonna do it both ways. So what we're gonna do is we're gonna put things in terms of theta first, and we'll go back and we'll do it in terms of x and y, just to show you the two different ways to do it. So let's make this substitution here. Let's make r equal to x cosine theta as our substitution. Let's start with that and see what we get. So this equation is gonna become k integral lambda. We leave this as dy for now, but we're gonna do something with this equation, or this equation actually. cosine theta, and r squared. So r squared is going to be like x squared in the denominator, and then cosine squared in the numerator. So I think you're going to get something like this. Does that look right to you guys? I mean, for now it looks nasty. Let's see what else we can do, though. So now x is a constant. We don't really... This is fine. We can pull this out of the integral lambda. So now we just need to deal with dy. What's dy equal to? We could use this equation, right? Let's say we want to put dy into d theta. Here, we'll do that one later. So if I know that r sine theta is equal to y, what's dy d theta going to be? R cosine theta? Yeah. But remember that, actually, this isn't the right answer. Yeah, there'd be a d theta, but this isn't the right answer, actually. We've forgotten something. R isn't constant, right? So we can't really do that. We need to replace the r right here, right? Well, luckily we have this guy right here to do that for us, right? X over cos theta, yeah? So let's plug him in here. So it would become x sine theta divided by cos theta. And now this isn't dy now, this is just y. All I've done is just make a substitution, right? Okay, x sine theta over cosine theta, though, is x tan theta. And I see someone is already writing the next line, because now if I do dy, we get x secant squared theta d theta. Okay, so there's our dy now. And now we only have one variable, right? If we plug everything back together. Okay, this is kind of an aside. That's our substitution stuff that we're doing. So now what we have is k. Remember, x squared and lambda can be pulled out of the integral. They're not varying in this problem. And we have left over integral. Dy was equal to x times the secant squared theta. And I'll put this all together. So cosine cubed theta, and then our d theta is still sticking around right here. So what originally looked like something complicated, cosine cubed, looks complicated, right? But it turns out that secant squared times cosine cubed, you're just going to get... I'm going to do x over x squared. We're going to just do 1 over x right here. What do we have left? It's literally just cosine theta now, right? It's just cos theta d theta. That's all that's left, right? So that's actually a really simple integral. It's a really simple integral. And I'm doing it in this way as a hint to those of you guys that might be working on the lab manual problems. I think it's the very first lab manual problem that I gave you. I think the number's 271. I don't know. But it does involve a rod like this. And I would highly recommend doing it with angles because it makes it better. Where would the bounds go? Yeah, let's talk about the bounds. Let's talk about the bounds. What would the bounds be? Where'd the square go? Let's see. The x squared? The x squared was, when I plugged in for dy right here, I got another x, which canceled out with this x squared. So k lambda over x, and we're just an integral, so. Yeah, what would the theta bounds be? Yeah, the y bounds would in fact be negative a to positive a, right? Now there's two ways you can do this. You can either do the integral and then convert theta back to y, which would be by doing, I guess, this one here. That's your option. What you could do is you could say, do the integral first, because it's a simple integral. You're going to get, you know, sine theta d theta. And then to do the integral, what you'd do is you'd replace sine theta with something like this. But I don't like doing that. People are also mentioning this integral is going to be, it's going to be, what's the word for it? It's kind of symmetrical, right? So we can really just do half of the integral if we want to. Right? So what I'm going to do is, I'm going to say that our integral is going to go, what we're going to do is we're going to do the double the integral trick. I'm going to say it's going to be double the line, when I draw the line from dq at the origin, the angle is going to be 0, right? And we're going to go from 0 up to here. That's going to be our limits. So all we really need is the angle at the apex of our thing. the angle at this point right here. And all I can say, and I'll write it right here, is that our maximum for our angle right here, I kind of want to just call it theta max. The only way I can really write this is in terms of x and a, right? By using arctangents. Arctan of a over x, right? That's our maximum angle, basically, right? And we're just going to plug that in right there. Theta max. What is dy for? What's your question, Jean-Wei? Or Jean-Ye? What is dy for? dy represents like the kind of thickness of the cut that we made here, basically. Does that answer your question? And we can't go from 0 to pi over 2, by the way, Tyler, because 0 to pi over 2 would be like... pi over 2 would be when the angle was like straight up and down like this. And that would be if the rod was infinitely long. We can do that at the end. We can take the limit if we want. Okay, let's finish this this stuff. Do you guys have any questions? I'll slow down for a second. We did a lot of algebra. Did a lot of algebra. And a lot of kind of trig and calculus stuff here. So if you're lost, I understand. And, yeah. Jose said you could bring it back to y, so that's an option, yeah? Yep. At the end, we'll do x greater, much greater than a if you want to, sure. All horizontal meowers, you're saying the pi over 2 situation? Oh, for just the answer? The answer will be all horizontal, but that's because the dy's or ey's are going to cancel out. All right. So I think x much greater than a would probably represent just a point charge, right? I forgot the square on the x in the last equation I wrote. Did I? I think I got it, because there's an x right there and there's an x squared here. I appreciate you mentioning that, but I think this is right. Also, dimensionally, I know this is right, because the units are k times charge per unit length, so this gets back to the right units of kdq over r squared. You need to have charge in the numerator, length squared in the denominator, and then you need to have k. That gives you the right units. Remember, the unit analysis, dimensional analysis is always going to be really helpful. All right, let's solve this integral. I gotta scroll down a little bit. I can't write on the bottom of my pad here. So we're gonna have ex is equal to 2 lambda divided by x. Doing the integral of cos theta d theta is gonna give us sine theta, and we're gonna evaluate that between 0 and theta max, which we already said was the arctan of a over x. Now this might look scary here. Hopefully it doesn't. Hopefully you did enough in your guys' trig or pre-calc or calculus 2 classes that this doesn't scare you too much. So we're going to get 2 lambda divided by x, and then we're going to have the sine of the arctan of a over x. Now, maybe you guys can tell me in the picture. This is evaluating this piece is something where I think it helps to think about a triangle. We actually kind of have one already. Maybe someone can figure it out. What's the sine of the arctan of a over x? Now, this is where it's a good idea to visualize which angle that is. Can you visualize it without me drawing it? Imagine I draw a line from here to here. Gotta hold down the Alt key. Imagine I draw a line from here to here. I think that Mendonça has it, actually. I think that's the right answer. We want the sine of that angle, right? The sine of the angle that's made down here at the bottom when theta is maximum. The sine of that angle is, I think it's a divided by, yeah, he got it right. Tyler got it exactly right. Can you guys see what he wrote? He wrote a over root x squared plus a squared. That is the sine of this angle, right? Here. What you can do down here is we can basically we can draw a triangle real quick. Right triangle. Can we draw a right triangle? Nope. That's not a very helpful tool. So I'll do a free formed. Oh, the k got dropped. You're right. I'm sorry about that. The k should still be there. Thank you. So basically, what we have is we've got a triangle. We know from the way this is written that the sides of this triangle are a on this side and x on this side, and this is the angle that we're interested in here. Call it phi, theta max, whatever. And we know that the sine of that angle is going to be x over this side, and this side has the length of a squared plus x squared. So what we end up getting here is 2k lambda divided by x multiplied by a over the square root of a squared plus x squared. And that's effectively our answer, except now one more thing we have to do is we need to go back and say we said here that lambda was equal to q over 2a, right? So we need to plug that into our equation. So we end up getting as a final answer, oh my bad here, I should have moved this down. That's what I meant to write. So for our final answer, then we're going to get ex is going to be equal to, we're plugging in q over 2a for lambda, so it's going to be 2k q over x 2a, and then what's left? A over square root a squared plus x squared. And that's going to be equal to, the 2's cancel, the a's cancel, so we just get k q divided by x square root a squared plus x squared. This is actually the final answer, and we'll talk about why, but that's basically it. Okay? Do you guys have any questions? We broke our object up into little pieces. We figured out the electric field created by one of those pieces. We split that electric field up into x and y components. We just solved for the x component. That's all we've done so far. Anyone have any questions? While you guys are typing, I want to mention one other thing. I didn't say anything about the DEY in this case, and the reason why is because this problem is completely symmetrical. If I were to calculate DEY, what I would find is that the components above would cancel out with the components below, and they would all add to 0, basically. Right? That's what happened. Is that all the y components for objects above the x-axis, right, would point downwards. All of the components from below the y-axis, or below the x-axis, would point upwards. And so the DEYs would basically add to 0. Alright, so this ends up being the final answer, actually. That is the final answer. If we really want to improve exactly how we write it, what we would do is we would say it's points in the x direction, and then we would just eliminate this, and then we could put a vector symbol on top of it. Right there. That gives us the electric field due to a finite length line charge, as long as the point that we're describing is in the center. You guys have a problem where you have to do a point that's kind of out here, basically. And I think you might have a problem where you have to do one that's like on the same like point of the line. Okay. Anyone have any questions? Did you guys follow that okay? Okay. I mean, we're going to have a video up so you can obviously review it. Also, the steps in the problem that we did are, yeah, the two that showed up in this line suddenly right here was because what I decided to do was, instead of taking the integral over the entire length, I decided to cut it in half and only do the above portion and then just double it. So if I had not put this in here, what I would have had to do is I would have had to put like negative theta max to positive theta max, right? So instead what I did is 0 to q and then just like, you know, doubled it. The last two down here, in case that's what you're asking about, that came from the definition of what lambda itself is. Lambda is equal to q over 2a. So they ended up canceling out. It's a nice problem. It's something that when I first took this class, I remember the summer before I took an E&M class for the first time, that I went and got a textbook, and I read the first chapter, and I was like, I really understood that. I was like, I really feel like I know what electricity is, or at least static electricity. I understand Coulomb's law, and I understand. And then I tried to do like one of the first problems in the back of the book, and I couldn't do it. And I was like, okay, clearly I have no idea what I'm doing. So these problems are pretty challenging. There's no doubt about that. And this is one of the easier ones. I'm going to mention that on your homework for the lab manual, what you're going to see is there's going to be one change, and it's going to have a pretty substantial impact if you don't know what's going on. The one that's on the lab manual homework, the value of lambda, okay, is something like k times x squared. It's not the same k as this, which is confusing, but whatever. Lambda is like a function of x, basically. Right? Lambda is going to be a function of x. So it's going to be like x squared when you plug it in here. And I mean, the only effect that's going to have is just you're going to have some other variables show up when you're doing it. And it actually makes I think it makes the integral like stupidly challenging, but I mean, that's kind of something for you guys to work on and build your skills. But let's talk about extreme cases of this. So we can look at limits in the case of like kind of what happens. So we can ask, for example, we've got a line of charge now, right? And what we found was the electric field at this point. Remember, this was x and this was a, right? This distance is x here. So what we can ask is, what happens if, let's see, x is much, much greater than a? That was your question, right? What happens to this formula when x is much, much greater than a? So here what we can do is we can say, well, if x is significantly larger than a, we can basically just neglect a and say x squared plus a squared is pretty much just going to be x squared, right? But then we're square rooting it, right? So what happens then is that the electric field ends up going to basically just k times q divided by r squared, or not r, sorry, divided by x squared, which is effectively the field of a point charge, basically, right? The electric field. That seems reasonable, right? If you imagine that we take this length x and we go really far away to some point over here, then at that point, it's going to look like the line has become point, right? It's a fixed length. There's another option where we could see the reverse. I think this works. So what happens if we do the opposite? If a is significantly larger than x? What would this reduce down to, you guys think, if I take a to be bigger than x? Like, way bigger. What do you guys think? What would this mean? This would mean x is tiny. So you're like right up here, right next to the rod at that point. It'll look like an infinite line. That's right. If you get close enough to this object, it's going to look like it's infinitely long, right? It's going to look like it's infinitely long. So, in that scenario, if we make a much, much bigger than x, what happens to the form of this? Meowers is saying kq over a. I know that can't be right because it doesn't have the right units. If you said kq over a squared, that would be possible. So you're close, though. What would it be? So if I make a much, much bigger than x, can I go through the limits? I'm sorry, what do you mean? You want me to go back to the one we just did here? limits? The limits on the integral? No, it's not kq over a. I'm saying it's wrong. It has to have the form of k times charge over length squared. Does that make sense? It has to have this form. That's right. I think that's right, Tyler. I think that's right. So if we make a much, much bigger than x, we basically just neglect this term, right? And we have square root of a squared, which is just a. So I think that if we make a significantly bigger than x, what we get is e equal to kq divided by x times a. That's exactly right. There you go. That's the answer. Can you guys see that? We can even go farther. You don't see that. Well, if a is significantly bigger than x, if I do a squared plus x squared, it just becomes a squared under the denominator, under here, right? So just basically let this go to 0. Not x itself, but within the thing here, make it go to 0. And then you have square root of a squared, which is just a. So you have kqx and then just a, basically. Because it's not x plus a. Look, if I say this, then x plus a goes to a. But x times a just goes to x times a. X isn't 0, exactly. If you put x equal to 0, you get infinity, and that's fine. You should get infinity if you go to 0. But, yeah, that's the idea. Yeah. Good question, for sure. I understand why you think that. That's definitely... Now, there's another way we write this, actually, usually. Usually what we do is we say, well, q over a, if we think back to what we were doing in the problem, right? We had said that lambda was defined as q over 2a, right? So if I multiply the 2 over here, 2 lambda is equal to q over a, right? So that means, in my thing that I have right here, what this becomes, and this is the answer for an infinite line of charge, which will be something that will show up, you end up getting e equal to 2k over x, I think, right? Another way this is commonly written is lambda. No, I'm being stupid. Ignore what I just wrote. Sorry to confuse you guys. Let me go slowly. It's when I talk and I write at the same time that I make a lot of mistakes. Q over a is 2 lambda, right? So q over a here becomes 2k lambda over a. There we go. That's the answer. I was like, there's something missing there. X. There we go. That's the result for the infinite line of charge. You replace q over a with 2 lambda. So there's the 2 lambda. You leave the k and the x inside there. We're going to derive this tomorrow, or like next week. But, or meet Thursday. Right, we meet Thursday. Infinite line of charge. We're going to derive this using Gauss's law in the future. But, all right. Do you guys have any questions? No, next week. I'm sorry. Like this week we'll have like an hour meeting on Tuesday. Yeah, I was thinking of my other class, which doesn't meet Monday, right? Yeah, but we'll meet this week on Thursday for an hour, and we'll meet again next Tuesday. We'll have our class isn't getting disrupted by the break. That's right. Okay. Do you guys have any questions? So we can actually visualize what this field looks like, by the way. I'm going to pull this up so we can kind of do this for all the things we're going to do. Not with this guy, but this right here is posted on your on Canvas. You can find it right here. It's Electric Light Simulator 3D. And what we can do is let's stop and look at what it's doing right here. I want to change this. There we go. I think that's what we want. It's one of these two: field lines or the vectors are good too. Let's do vectors. So this is the electric field of a negative point charge right here. Right? See all these vectors pointing inwards? You can see that it's actually 3-dimensional. Right? Unlike the ones that I was drawing. So that's a point charge, right? So what does a line charge look like? Well, this is what it looks like from above. is what it looks like from the side. And all of that stuff is generated from that one equation we just derived. Except this, I think, is an infinite line. I think you can change it to a finite line. There it is. That's the one we just derived. Right there. And if you change it to field lines, it gets really crazy. Now it's like, this is what it looks like from above. Oh, I can't get it to get on axis. It's kind of like a spider web from above. But when you turn it sideways, you get this. Where's the line? I think the line's right there. I think the line's right there. You guys can play with this stuff if you want to. Yeah, the line is... Right now, the line is kind of coming out of the page at us. And those are the field lines, kind of going out like spider webs. And if I rotate it 90 degrees along the axis towards you guys, that's our electric field. That's quite literally what you would get if you take the equation that we just drew. Really, it's really this one. If you take the equation that we just derived, right here, without getting rid of these black lines, you take this equation, and you pick every single point in space x. And at that point in space, you draw your vector for the electric field. Except that we only derived it for one point, right? So you'd have to come up with a generalized answer as to what the electric field was at an arbitrary point. This is what you're going to do on your homework. Like down here or down here, for example. And if you did that, you generate this picture right here, this vector field. I think it looks pretty cool. I think it kind of like make you dizzy looking at this stuff, or make your brain kind of shut off. I don't know. But I like this version better. And then if you do infinite line, which was the one we started with, where is it? That one is much more symmetrical. Okay. Can I assume that the field is at every point around the charge? Yep. There's a value for the electric field at every point around the charge. That's right. That's right. Okay. Do you guys have any questions? This one represents all points in space for the infinite line. Any questions at all? You guys want to take a break? 12-minute break? Alright, we'll take a 12-minute break. We're going to start again at 7:15.